Best handwriting incoming. Oh, look at these well-formed letters. Hey, will you kill the light while you're back there? Would you shut the light off also? Let's work in the dark. Oh yeah, that is nice. So I gave you graph paper because you're going to need graph paper. I have six examples. So you'll use six of the eight that I gave you. And if there's any more, if I call an audible, then we can have a couple backups. The homework assignment will already have the grids on there, so you don't have to worry about that. But these are for your notes, the ones I gave you. So I need to bring in a grid. Hmm, I like this. Oh, no, I don't like it. This one. This one, no good. This one. Oh, yeah, that's much better. Have you guys ever graphed a quadratic before? I mean, you probably would have done it with me since I was your algebra guy. So let's chuck one up there. So I have these scripted in a very particular order. The first one we want to graph is this one. So back in Algebra 1, when we learned how to graph, we graphed straight lines. And earlier, maybe a couple of weeks ago, you graphed absolute value curves, not curves, but absolute value V's. So this is a new family. I mean, it's not a family that we're unfamiliar with. We've worked with quadratics. We know how to factor them and use the quadratic formula and complete the square, stuff like that. The next couple days, few days, quite frankly, are dedicated to making their graphs. And so we're going to start with this one. Every family of functions has one like this that's unmodified, and this is called the parent function. And every quadratic is a variation on the parent function. So that's why we want to get this one out of the way first. And the thing we're going to do to make this make sense, first off, is we're going to make a table of values. We need this first one to make sense, and we're going to learn some stuff from the parent function. We won't generally make a table of values, although making one or knowing how to make one is what gets you over the hump. When you get stuck on a graph this year, next year, first year of college, whatever, you can always make a table. And the table is always a matter of just pick some X's, put them in, and see what you get for Y's, and then play a fun game of connect the dots. So I'm going to have some values that I want you to do. So I'm going to be a little bit bossy with this rather than take your input. We're going to do 3, 2, 1, 0, -1, -2, and -3. And by putting these particular values in, we're going to see the relationship, the shape of a quadratic. Does anyone know what the shape of it is, by the way? Have you ever seen one? No? You? Yeah, it's called a parabola. Very good. So the shape of any quadratic when we graph it is called a parabola. And yeah, it's like almost like a bowl or a U shape. And it can even be flipped upside down to look like the St. Louis Arch or something like that. So the first one is the most basic. And again, this relationship that we see is what drives our success for the next couple of days. So pay close attention, and I'll try to draw your attention to a very particular relationship here in a moment. So first part of this lesson is like fifth grade difficult. So here it goes. We're going to take the x's and put them in place of, well, the x right here and do math. So if I put in 3, what's 3 squared? Good. So there's our first point on the graph, 3, 9. Right. So you can graph the point now if you want to, or you can wait and graph them all later. I'm going to hold off. Let's keep doing math. If we put 2 in there, what do we get? 1, 0. Good. And then what about -1? Good. So it goes back kind of like an absolute value graph. It goes back to being positive again. And what about -2? 4 and -3. Good. So we're going to see some real nice symmetry here. You can tell there's going to be symmetry from the way those y values come down in the same pattern as they go back up. So take, I don't know, 20 or 30 seconds here. And let's go graph the points. So I'll do that up here. I assume you all know how to graph points. So there's our first couple. So that's 3, 9 and negative 3, 9. And then there's 2, 4 and negative 2, 4. And then there's 1, 1, negative 1, 1, and 0, 0. The hardest part of the lesson, I mean, there'll be some sort of tricky math that we do here in the next 20 minutes or so, but the real difficulty once you nail the math is trying to make the graphs look right. So when we graph this quadratic, we want to make it look like it's a smooth curve. And so usually what I do, and I'll mess up and you're welcome to laugh at me, but when you use a pencil, it's good to sketch first real lightly with your pencil. And then when you feel like you've got a good graph, then it's good to go back over it. So I'm going to go over this. Um, I only get one shot at this. I mean, I've got an eraser just like you do, but mine is going to get hit with the ugly stick here pretty bad. So, oh, good God. So I suppose that will do for a beginning of the Tuesday morning approach. So this is what the parent function looks like, and all other graphs that you see for the next day or couple days are going to be variations of this. Some will be fat, some will be skinnier, some will be moved around, some will be flipped upside down, some will have all of those transformations on them. We move left, we move right, we flip it, we make it thin, we make it fat, whatever the case may be. So do you have any questions just on the parent function? The essential point for today, the real meat and potatoes of today's lesson is this point right here. What's that point called? That red point? It is the origin if we were just talking about the x-axis and y-axis, but as it relates to the parabola, do you know what it's called? It starts with a V. You know this word. It's called the vertex. And every parabola has a vertex. And a decent share of our time today is going to be spent finding the vertex. Like that's the hunt is can I find the vertex? Um, okay, good. I want to make sure that I was recording here. So any questions on the parent function? Okay, so head to a new graph. I'll make a new page and bring in a new graph. And now what we're going to start doing for the remainder of the period is we're going to start doing variations on the parent function. So I'm going to clone this page a bunch of times. There we go. Oh, I should have moved this first. Oh, well. All right, so our first one that's going to get modified is this one. I don't really think I can stress enough with my limited sleep and energy right now the importance of this first step, but here it goes. This is my attempt. You have to know how to find the vertex. We kind of know already what the graph's going to look like. The thing is, I don't know where to go to start it. And what I could do is just start making a table and pick a bunch of random X values. The trouble is, if you pick the wrong X values, you could have a hard time perhaps finding the center, the vertex. Or you might pick X's and they go way off the graph, like you get a Y value of like 31 or something like that. And so this portion of the lesson is dedicated to just helping you find the vertex. And so really important that you write down this little formula. The vertex can always be found at negative b over 2a. And we know who a and b are because we've seen them with the quadratic formula before. So negative b over 2a is your go-to. This is one of those things that you want to put in a box and highlight it about 94 different colors. This is the formula that we'll always use to figure out like what's a good starting point because I need to know how to make the graph. And so in this particular red quadratic up here, what's a? Nice. What's b? Nice. So you do have to do some basic math in this first step. You can't mess this kind of stuff up. You know, by mid-March of your Algebra 2 year, can't be messing up fundamental arithmetic. So this is the opposite of b divided by double a. So if we plug in these numbers into this handy-dandy little purple box here, what's the first thing we would get on top? 6. Very good. So we'd get positive 6 because that's the opposite of b. And if we divide by double a, what's 2 times 1? And what's 6 divided by 2? Good. So here's what we know right now is that the vertex is at 6 divided by 2, which is 3. comma something. You should ask if you're not sure how I did that. That's just the opposite of b divided by 2a. It doesn't give me the whole vertex. It gives me the x coordinate of the vertex. In math, what do we always do if we know an x and we want to find its corresponding y? Plug it in. It's always the right answer. Plug it in. So take 3 and go back up here to where these little yellow arrows are pointing and change both of those x's into 3's. And you can show your work on a step like this. I will, but you don't have to if you think it's something you can do in your head. But if I change this first x into 3, 3 squared is 9. And then in the second part, what's 6 times 3? So I have 9 minus 18 and then plus 5. And what's 9 minus 18? And what's negative 9 plus 5? That's huge. So we now know where to start the graph. So we're going to go to the point 3, negative 4, and we're going to put our first point. So that means right 3, 1, 2, 3, down 1, 2, 3, 4. Now, what I want to do here is I want to save you a bunch of time. This is the second critical part of today's lesson is, okay, so I got there. The question is, how can I find more points? You can always go and make a table, but I'd like to save you some time and tell you that you don't have to do that. So I'm going to go back to the first graph that we did, and I want to show you some relationships. Incoming, very important information. Don't doze off for the next minute or two. Well, don't doze off at all, but especially not right now. So the critical relationships with quadratics are like, how do I build them? And so I want a shortcut. I don't always want to have to make a table and plug in x's and find y's. So what I want you to notice is, I'm going to zoom in on this a little bit. I guess that's a lot bit, but that'll work for me. Do you notice how I went out 1 and up 1? So that's our first relationship that we have to memorize is out 1 is up 1. When we went out 2, you see where I'm squiggling there? How far up did we have to go to hit the graph? 4, right? And then let's look at another relationship. When we went out 3, so we squiggle away from the vertex out 3, how far up did we have to go to find the graph? 9. And even though we don't have enough room on these grids, if we went out 4, how far up would we have gone? Good. So back to this other page. What we want to see about this, oops, am I on the wrong? How did I get down there? That's weird. The relationship is if we go out 1, we go up 1. If we go out 2, we go up 4. If we go out 3, we go up 9. Notice I'm not saying right or left. The reason I choose the word out is because I'm going both right and left. Parabolas have that mirroring sort of characteristic. So going out is my way of saying go left and right. Do one on each side. So the point is this, that rather than make a table of values, you actually already know where all of the other points for this parabola are going to be. Let's take a look at them. So if we leave the vertex and we go out 1, where do we go? Up 1. So you now know that there's another point right here and right here. You don't have to make a table to prove it. What if we go out 2? Go up 4. Notice I'm not going out 2 further from where I was. I reset back to the vertex when I do a new journey. So I'm going to go out 2 and up 1, 2, 3, 4. So I now have points here and here. You should always graph your points 2 at a time. No sense in doing them like twice. And then the last one that's going to fit on this graph is going to be out 1, 2, 3, and then up 1, 2, 3, 4, 5, 6, 7, 8, 9, like this. And again, if I had planned a little bit better, I would have moved this vertex down a couple notches and we would have been able to go out 4 and up 16. But we don't have enough room on this particular grid, so we're going to make do with what we have. So once you have enough points, my rule is plot as many points as the graph will allow. With lines, I don't say as many points. I say make sure they're far apart. With parabolas, you literally need every point you can get your hands on because every point is a little piece of skeleton to hang stuff on. And so now your job is to the unenviable task of trying to make the graph. And what you're not allowed to do is go like this. You can't go straight line, straight line. Like that's not, you can make it look sort of okay, but eventually you're going to get busted on that. So what you want to do is try to master the fine art of creating that curvature. And it is not simple, and it is often quite ugly and quite clumsy. But that's the goal, is find the vertex and then build the graph from the vertex. Any questions so far? Okay, let's head to our third example. So for this one, I'm going to place a modifier on the parabola. You'll see. So we're going to do y equals 2. Ooh, yikes. 2x squared plus 4x minus 3. So what's our happy little dandy formula? What do we do? Negative b over 2a. Jackpot. That's going to be like our battle cry here today. Negative b over 2a. Some people think of it as opposite b over 2a. Then we don't say something like, oh, that's always negative. Like it's the opposite of whatever it was. What's a? What's b? Good. So again, I think the math is pretty simple. Does it get messed up? It does. Really shouldn't. So if we do the opposite of b, that's the negative 4. And if we do double a, what's 2 times a? And what's negative 4 divided by 4? Perfect. So we now know the vertex is at negative 1 comma something. Okay. That's huge, but it's not enough. Like the yay whoop-de-doo. I know horizontally where the vertex is, but like that's not going to get me anywhere. That's not going to get me close to the finish line. So what do I do now? Plug it in. And so wherever these little red arrows up here are pointing are x's, those are inputs. That's where you put your x, your negative 1. The order of operations demands that we do things in a certain order. So the x squared right here in this little jelly bean has to go first. What's negative 1 squared? 1. What's 2 times 1? Perfect. So we have 2. And then what is 4 times negative 1? Negative 4 minus 3. And then basic math. What's 2 minus 4? Negative 2 minus 3. So we now know the vertex is at negative 1, negative 5. Now, don't be hasty this time. I would appreciate the sentiment if you went ahead and felt ambitious and started graphing, but the trouble is that this graph has a modifier. So it's not going to build according to the same principles as its predecessors did. So we are going to still, though, go to the vertex, which is at left 1, down 1, 2, 3, 4, 5, which is right here. So if you would just kind of watch the TV here, I'm going to do some pretty high-grade vandalism here. Here it goes. None of this stuff matters anymore. That was all important for getting to where we wanted to be. That was like getting to the build site. But now we need to actually build the graph. And the 2 is the modifier that we place. Would anyone like to guess what modifications the 2 makes to our build? It actually makes it skinnier. And listen, intuition would tell you that with the 2, it should get fatter and stouter. But what happens is all of our outs and ups, our outs stay the same, but our ups get modified by 2 times 2. And so I'll write this down for you. You can write it down too. Because of the 2, when we go out 1, we would normally go up 1. But if we double that, we go up 2. When we go out 2, normally we'd go up 4. But 4 doubled is 8. Follow? And we won't have enough room for this one, but let's make sure that we're all on the same page. If we went out 3, we'd normally go up 9. But we double that and we get 18. And again, we won't have enough room for that. So we're only going to be able to graph 5 points, the vertex and then 2 on each side. And then we're going to run out of real estate. And I could do something sadistic, like have you rescale your axes by 2s or 4s, and then we could fit a bunch of points, but we're not going to worry about that. Because our grids go by 1s, then we're out of space. I don't have enough room to go up 18. I could go up 15 or 16 from here, but not 18. So we're going to make our points now. And I'll zoom in a little bit on this here. And again, you've written this down. So if we go out 1, we go up 2. And this does, in fact, have a skinnying effect. It's sort of counterintuitive. We feel like the big number would make it bigger, stouter. It actually thins it. It's called a vertical stretch. When we went out to, how far up should I go? 8. Again, normally would be 4. We're going to double that 4, make it 8. So out 2, 1, 2, 3, 4, 5, 6, 7, 8. And I'm not even sure that I want to try to graph this one, especially not with you watching. But I will say and you'll learn this through experience, that the skinnier your parabolas get, they are a lot harder to make look good. And that's just between you and a pencil and a really light touch. If you're an artistic person, you'll struggle probably less. I still, to this day, man, you'd think after 3 decades of this that I'd be a master at it, but graphing skinny parabolas, meh, no thanks. So anyways, do your best, connect the dots. Always remember to make it look as curvy as you can. It does not, by the way, here's one of the criminal offenses that you cannot commit. I do see this all the time, and you will lose points for this. I'll try not to be too harsh on your graphs as far as the artistic quality, but this is something that can make you lose points if you do this. What's wrong with that? It can't come back inwards like a horseshoe. These graphs are always working their way outwards, despite the fact that they sometimes look like they're going straight up and down. They never are, but our graphs almost look like it sometimes. But the one criminal offense that I won't let you do is to have it curl back inwards. And I do see that more than I care to admit. So when you graph it, try to just continue it upwards like this. Okay. And I don't really have any expert pro tips other than just use a light touch first. And then once you're happy with the graph, then you can go back over it. But going at it full send on the first first attempt, that's a little bold. Any questions so far? Halfway home. Right, for our next one, we're going to throw a new modification on the parabola. And then the last couple after this, we're going to throw fractional modifications on there as well. So this one is this mod. Our little battle cry is opposite B divided by 2A. If you're a person that makes fractions sideways like this, you need to stop that like a year ago. Okay, fractions should be vertical so that everyone understands what's on the top and what's on the bottom. So no diagonal. Those are fine like when you're just sketching like a recipe for chocolate chip cookies or something at home, but in math, fractions should always be straight top, straight bottom. Okay. All right, what's A? It is -1. What's B? Nice. This formula just won't fail you. I mean, you can fail it, but it won't ever fail you. So what is the opposite of B? -2. And what is 2 times A? 2 times -1 is -2. And what's -2 over -2? +1. So we now know the horizontal location of the vertex. But I mean, if all you told me was that the vertex is at 1 something, I'm like, well, it's not really, I mean, thanks, but thanks for almost nothing. I mean, I don't know where it is. So again, we're going to put 1 in place of the x's to figure it out. Common error incoming if you're still awake. This is not +1. Why not? Because there's a negative in front of the x squared. The order of operations demands that you do this yellow blob first. Very, very common misconception is that people think, oh, it's -1, and when I square it, it becomes +1. It's a bunch of hullabaloo. You put 1 in place of x, what's 1 squared? And then the negative comes on as an afterthought, and you get -1. Okay, that negative in front of an x squared is an afterthought. It doesn't get squared with the x. And then it says plus 2 times, well, 2 times 1 is 2, and then -4. And then you got to do little kitty math. What's -1 plus 2? What's 1 minus 4? So we now know the location of our vertex is at 1, -3. Huge. So again, we're going to go there and we're not going to waste a bunch of time by making a table of values. We should feel empowered like we could if we needed to, if we forgot, but we don't want to. So I'm going to go to the vertex, which is at 1, -3, and I'm going to put a point. What do you guys suppose? By the way, here I go again. The great pen of vandalism is about to do its thing. Are you ready? Here it goes. Here it goes. It's going to go down. Right. However, it doesn't get structurally changed because the negative is like a -1. So it doesn't have any effect on like stretching the graph. It just causes it to go upside down. So I'm going to zoom in on this again, and we're going to head to the vertex, and we're simply going to follow the same relationship, only we're going to do it in a downward direction. So when we go out 1, we're going to go down 1. We're keeping the relationship intact. When we go out 2, where will we go? Down 4. Good. 1, 2, 3, 4. And again, we don't quite have enough room here. If we were to go out 3, 1, 2, 3, we'd go down 1, 2, 3, 4, 5, 6, 7, 8. I could fudge it a little bit and sort of estimate that the points are going to be right about there. It's a little cheaty, but it works, and it gives me a little bit more structure to hang something on. I like that. So now we're going to make a sketch. And when you return to a normal parabola after having graphed a 2 times skinny parabola, it's kind of a nice welcome. Ooh, that one came out really well. Oof. Get your eyes on that sucker. Man. All right, we're almost there, guys. The final modification. Do you have any questions so far? The final modification is a fractional modification. And those of you guys that struggle with basic math on fractions, you might feel a little burn. Well, let's find out. It's your job to ask. It's incumbent upon you to advocate for yourself. If I do any calculations and you're like, whoa, 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 it's just, you just got to speak up and ask. So we'll start with this one. Our little formula is worth writing down. I feel like writing it down every time is not a terrible thing. It takes like 2 seconds. What's A? Yeah. What's B? Good. Again, the formula, the purple formula will never fail you. It's not to say you won't boof it maybe periodically, but it never doesn't work. Purposeful double negative there. Never doesn't work. So the opposite of B goes on top. What's that? Perfect. And then watch out, basic skills. And this is where maybe a few of you might need to speak up and get a little assistance here. We have to double A. So this is where we assume that you understand how to do 2 times a fraction. What is 2 times a half? 1. Okay. When you do double A, you have to go back to what your old teachers years ago taught you that, okay, 2 times 1/2 is 2 over 1 times 1 over 2, so on and so forth. So any questions on that? Okay, what is -3 divided by 1? So we know the horizontal location of our vertex is at -3. And again, fifth verse, same as the first, well, fourth, I guess, because the first one we didn't do this, but we're going to take -3 and we're going to put it where these little yellow arrows are pointing. And as always, you got to do math. So if you do the yellow jelly bean first, what is -3 squared? 9. What's half of 9? So we get 4.5. And I'm okay with that kind of decimal, 4.5, 4.5. That's not the kind of decimal that keeps me up at night. If it was like 4 1/3 and you put 4.3, then yeah, it's not really, wouldn't hurt anything, but it's not perfect. But 4.5 is perfect. And then we got to put -3 in place of the second yellow arrow. What's 3 times -3? -9. So I'm just going to put -9. And then you have to math. What is 4.5 minus 9. Mm-mm. Negative 4.5. And what is negative 4.5 plus 1? Negative 3.5. So apologies for this, but you know what? It was going to happen eventually. We've got ourselves a tweener. I like to call points tweeners when they don't lie on lattice, when they don't lie on grid lines. And so it's okay. We'll suffer through this together. So step one is we're going to go to the vertex, and it's at negative 3.5. So I'm going to zoom in on that a little bit just so I can get a good beat on it. So negative 3, 1, 2, 3, negative 1, 2, 3.5 puts us right there. Okay, that's a tweener. Now, hadn't intended for this to be portion of this problem, but here it goes. We have, if I go back to the beginning again, the great pen of vandalism comes in, and at this point, I no longer have any use for this portion. Like all of that was just show me where to go. That's all that was. Now that I'm there, what do you suppose a half does? It does. And the reason it makes it wider is because it takes all of your y values and it cuts them in half. So the normal things we would do, we're going to do half as much. We're still going to go out 1, but when we go up, we're not going to go up the full 1. What are we going to go up? Half of 1, which is a half. This is the part where you might get lost. So I'm going to write this down. So if we go out 1, we go up a half. If we go out 2, remember, we normally would go up 4. What's half of 4? So we go up 2. If we go out 3, normally we'd go up 9. What's half of 9? 4.5. 4.5, 4.5. I'll be consistent here. We can do, I'm thinking we can do probably one more. If we go out 4, normally we'd go up 16. What's half of 16? So we go up 8. And that we actually, I think we could do one more. These fatty graphs, you can graph a ton of points. Lucky you. If we go out 5, this is our first time discussing this. How far up would we go? 25. But what's half of 25? 12.5. So we should have plenty of real estate to graph a buttload. It's not a mathematical term, a buttload of points. So here we go. So I'm going to zoom in. You wrote all this stuff down, I presume. So I'm going to get in there and get a good close look at my graph and let the games begin. So let's plot some points. So the green one is the vertex. All the red ones will be the new guys. And so if we go out 1, how far up do we go again? A half. So I'm going to go up a half. Our next points should lie right there. We're back to lattice points, but not for long. If we go out 2, how far up should we go? Up 2. It would have been 4, but we're taking half of 4. So I'm going to go to right here. Start with a tweener, end with a tweener. If we go out 3, we should go up 9, but we're not going to. How far up are we going to go? 4.5. So I'm going to go out 1, 2, 3, and go up 1, 2, 3, 4.5, which places us right there. And I do believe we're going to run out of space after the next couple. Out 4. How far up will we go? 8, right? It would have been 16, but half of 16 is 8. So we're going to go out 1, 2, 3, 4, up 1, 2, 3, 4, 5, 6, 7, 8. And we are again back to having a tweener. And then you can see that we'll be able to fit the last one. I mean, that's not very difficult math. If you start 5 below and you try to go up 12.5, you got room. So if we go out 5, so I'm going to leave the vertex and go out 5. How far up again will we go? 12.5, since it's half of 25. So we're going to go out 1, 2, 3, 4, 5, and then up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.5. And look, we're back to a lattice point. And you will find these to be more enjoyable. That's probably not the right word. They're better to graph. There's something more fitting with your pencil and your the side of your hand when you graph like this. Fatter graphs are easier to make. So let me get through the last example, and then we'll be done. And I'll probably hand out the assignment today, but tomorrow I'm guessing will be a nice day to work on it. So let's get through one more. Any questions so far? Right, the last one. This will be the hardest one, basic skills wise. So, but I mean, the what are we doing doesn't change. It just gets a little bit more difficult with harder numbers. So, the negative b over 2a is like I'm here as always. You know, what is a? Yeah, what's b? Nice. So if we plug those numbers into our handy dandy little formula, basic skills, hell incoming, watch out, okay? It affects some of us more than others. If we do negative b, that's not the hard part. That's 2. It's this part, 2 times a. Anyone know what 2 times negative 1/4 is? It's negative 1/2. And I will show that calculation here for anyone who wants to know and just doesn't feel like asking. 2 times negative 1/4 is the same as 2 over 1 times negative 1 over 4. And then you get 2 times 4 is 4. That's negative 2 over 4, which reduced is negative 1/2. And then there's a little bit more basic skills, nightmarish stuff to come. How do you do 2 divided by a fraction? You copy dot flop. So this multiplication problem in the white, this I called it division. I mean, I call it multiplication, but it's really division. But it becomes multiplication. It's really 2 over 1 times negative 2 over 1. And what's that? Nope. Negative 4. So like I said, the formula never fails us, but we could fail it by not knowing how to do basic things like make fractions and copy dot flop. So we now know our vertex is at negative 4 something. All right. So that'll be probably something that we have to talk about more as we go through this. So if we know negative 4 and we're going to plug it back in, it's going to go where the little yellow arrows are pointing, right here and right here. In this first one, in the yellow jelly bean, what's negative 4 squared? 16. And what's negative 1/4 of 16? Say again? Negative 4. Very good. And then right here, what's minus 2 times negative 4? Plus 8. And then what's negative 4 plus 8? 4 plus 1 is, we made it. So we know our vertex, and that's a lot of math. Again, easier for some of you than others. We're not all created the same. We don't all learn the same. So some of you will struggle more with that. You'll just have to talk to me. Anyways, I'm going to go left 4 and up 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Have my vertex. And then here comes the great pen of vandalism again. I don't need anything else. Everything actually that I need is just right here in this green box. That is my builder. What are the 2 things that builder is going to do? Go upside down and make it fatter, significantly fatter, because all my normal y values are going to get cut divided by 4. So when we go out 1, how far down will we go? 1/4 of a unit. When we go out 2, how far down will we go? Take the normal. What's the normal for 2? What's the normal for 2? 4. 2 squared is 4. So the normal is 4. What's 1/4 of 4? We're going to go down 1. If we go out 3, what's the normal down? 9. What's 1/4 of 9? 2.25, or 2 and 1/4 if you prefer. Decimals are fine here. Okay, let's do another one. If we go out 4, how far down will we go? So down 16 would be the normal. What's a fourth of 16? 4. If we go out 5, what's the normal? 25. What's a fourth of 25? 6.25. Okay. When I say a fourth, I'm just asking you to divide by 4, of course. If I go out 6, how far down should I go? 36. But what's a fourth of 36? And I don't think we're going to have enough room, but let's give it a shot just for shiggles here. If we go out 7, normally we'd go down 49. What's a fourth of 49? 49 divided by 4 is 12.25. So we have a bunch of points that we can graph here. So let's graph these and take a couple minutes and then we'll get out of here. All right, I'm going to zoom in a little bit. That's a lot bit. And here we go. All right, so again, we go out 1. How far down do we go? A fourth here and here. If we go out 2, how far down do we go? 1 here and here. You wrote all these down. If we go out 3, how far down do we go? 2 and a fourth right here. If we go out 4, how far down do we go? 4. If we go out 5, how far down do we go? 6.25 right here. If we go out 6, how far down do we go? 9. And just because we can, let's finish this off. And then we're officially out of room, especially on the left, but also we'll be out vertically. If we go out 7, how far down do we go? 12 and a quarter. Good. 2, 3, 4, 6, 7, 8. So it'll be right about here and here. And because class is about over, I'm going to leave the sketching of that to you, just like I think I did on the last one. Didn't mean for that to take 43 minutes, but as is the case, always math takes a long time to teach. So I'll go ahead and just hold on to the assignment and I'll give it to you tomorrow. Tomorrow we'll have a nice work day to graph some parabolas. Sound good? And if by chance you didn't finish your completing the square assignments, what a nice break that I'm not piling on today. Kind of accidental, but you could use the time to wrap those up since you get extra time.